Good afternoon to all of you. Maybe today I have some nose running problem, so maybe voice may not be very clear. So for maybe 2-3 minutes, just go through what we did in the last class, and then we will start. And if you have questions, any doubts, meantime you can ask. Yeah. No, in this year, yeah, so okay. Right. No, no. Again, you will have a mismatch. Of course, both of them, if you have quadratic, so it would be better, but still there would be inconsistent terms. So then theta z would become more like a linear one because of inconsistent constraint. So I'll repeat this question for everybody. So are there any other questions? Huh. Huh. Yeah. G, right, right. Right. Yeah, there is some kind of inconsistency here. So the displacement is then you can say what we assumed is kind of say centroidal axis displacement, and then you can get that displacement variation across the thickness from the expression for epsilon zz as del v by del y is equal to minus nu times epsilon xx. So you can actually get an expression for v which is varying along y direction. But because you don't still get independent strain epsilon yy, and so I mean we still go with taking v like as a constant throughout the thickness. So actually there were two questions. So one was on the consistent interpolation. So that I will summarize. I'll discuss when I summarize what we did in the last class. The second question was about the stress-strain relation we assumed for this beam problem. So see, we are when we are taking beam, what we are saying is that only one non-zero component of stress is sigma xx and sigma yy, normal stress in transverse direction and in the other transverse directions, sigma yy and sigma zz, they are 0. And based on sigma yy and sigma zz equal to 0, you get expressions for epsilon xx, yy and zz which are minus nu times epsilon xx. So whereas we assume the displacement b to be only function of x, that is, so what the question asked here was, see, when we considered this beam and say this is x and this is y. So when we took the displacement, we said that u is a function of course x and y both. So this side it can be written as u of x minus y times theta z, which is a function of x only, and then v we said it's only function of x. And based on this, if you look at epsilon yy is del v by del y. Since this is only function of x, so this actually turns out to be 0. But then when we use the stress-strain relationship, so there from the stress-strain relationship, what you get is epsilon yy is equal to see sigma yy, sigma zz are 0. So what you get is simply minus nu times where this nu is Poisson's ratio. I think I used mu, right? So I used mu for the Poisson's ratio, not nu. So this was mu. Is that right? I used mu for the Poisson's ratio. Nu or mu? So this is sigma xx upon E, and which is, I know this term is nothing but epsilon xx, so you get mu times epsilon xx. So see, this our displacement approximation tells us that sigma yy is 0, but then when it comes to the stress strain relationship, we are saying that no, epsilon yy is so much, and also similarly epsilon zz because of Poisson's effect. So actually then this quantity, when we come to this expression for this strain, needs to be reinterpreted, because no, there is a contradiction as of now, that this is 0 here, and then finally when we use stress strain relation, we are saying that this is non-zero. So then the reinterpretation of this is that this actually is the displacement of the centroidal axis y equal to 0, and now see if you what you can do from this particular expression, you can say that epsilon yy is actually del v by del y, and which is minus mu times epsilon xx, and which is depending on this model, you have du naught by dx minus y times d theta z by dx. And if you integrate this, so see you would get v as, now the first term, of course the mu would be there, and you will have here y times du naught by dx, and the second term would be y square by 2 into d theta z by dx plus a constant of integration, so let us say C1. If we now, rather than making use of what we got here, but now from the stress strain relationship we get this, and so you take that as del v by del y, and this is epsilon xx for this model, and so you get finally this, and now C1 you can say that v equal to this v, maybe now you can use v naught there, which is value of v at y equal to 0. So C1 will just come out as essentially actually this v. So this v is, let me write now as v naught here, and so then finally you can say that this v, which is a function of x y, is equal to this C1 is going to be equal to v naught, which is only function of x like u naught, and then of course minus mu times the rest of the terms here whatever we have got. So ultimately, although again you would see that still the stress sigma yy is 0. So what main assumption here is that sigma yy is 0, and based on this Poisson's effect, you can always see that you can work out, and you would get the v, which is actually function of y, but you would find that the variation due to this term and this term in v along y would be actually very less. So it's almost negligible effect when you if you now using this expression after calculating du naught by dx and d theta z by dx, and when you plot this along y, so this is of course the displacement of the centroidal axis, and the remaining term from top to bottom would be having very little contribution. So often we do not talk about this part of the, even in the books you won't find, most of the books you won't find this discussion on the variation of v transverse displacement along y. So what we are doing is, we are more or less taking v to be constant along y, so independent of y, and but still making use of the plane stress condition, that is sigma yy equal to 0 along y direction, based on the fact that the sigma yy, even if it is there because of distributed force, it will be much smaller compared to sigma xx. So there is a contradiction here. So maybe the better treatment could be that we say that this is a central line displacement, and then come to the first talk of the stress strain relation, and then work out finally this as your v here whatever you get. But as far as the detailed rest of the derivation is concerned, that is not going to change. So this was one question on contradiction of taking v to be independent of y and then saying that epsilon yy is minus mu times epsilon xx. So essentially the main thing what we are doing is actually using this plane stress condition, and therefore accordingly V is not getting modified, but it's not affecting the formulation here. Similar thing is there when you go to two-dimensional problems, plate bending problems. So you have similar situation there, similar to what we have in this case beams. So then next question I will answer in between. So let me, is there any other question? So see, last class we started with this shear locking, and what we said that the kind of element we were trying to formulate. So if we use the shear deformable finite element for modeling thin problems, it under predicts the deflection, and that phenomenon we call it as shear locking, say numerical modeling problem. So and then we said why it happens, what is the reason for shear locking, the expression for gamma xy, and which was in terms of minus theta z, and that was further written in terms of interpolation functions and so on, and dv by dx. And then we said we have some constraints when gamma xy, for thin beam gamma xy approaches to 0, so it leads to certain constraints on the theta z and dv by dx put together. So for this interpolation, finally the constraint puts a restriction that theta z should be constant within the element, and when you start from a boundary, everywhere you get theta z either 0 if it is 0 at the boundary. So beam does not deflect as per this numerical model. That phenomenon we refer to as shear locking. And then for the methods to eliminate the shear locking, we talked of three methods. Elimination of shear locking. So what I discussed was first one, which is consistent interpolation. So here see, the problem is coming in the the locking problem is because of if you look at the expression for gamma xy, theta z is coming as it is without any derivative, whereas we have a first derivative of dv by dx. So if we want to have a consistent interpolation, so what it suggests is that interpolation for V should be one order higher than whatever interpolation you are using for theta z. So last class I had said that if we want to eliminate the locking in this case using consistent interpolation of V and theta z, so when we formulate the element, so we have here say local element x and y coordinates, and this is node 1, and so we need to introduce minimum is, then we need to go for a quadratic interpolation for V, so we introduce the node in between. So say this is node 2 and then this is node 3, and when you and obviously then theta z should be linear. We cannot do the reverse way. So the question asked was whether we can have theta z quadratic and V as linear. It will not serve any purpose. See because theta z is coming without any derivative, whereas dv by dx is a derivative. So for the two terms to match, and therefore in the limit when beam becomes thin for this gamma xy to approach to 0, actually the interpolation of theta z and dv by dx should be of same order. So that means interpolation of V must be one order higher than theta z. So you have to take V, say in this case, as quadratic and theta z as linear, not vice versa, that theta z quadratic and V linear will not eliminate shear locking, and you will have the same problem what we get if we use linear interpolation for both these variables. So we had said that the degrees of freedom here, in case if you are having a quadratic interpolation for V, so the degrees of freedom corresponding to V would be V1, and of course if you are including the stretching of the centroidal axis, then you will also include U0, so which is same as what we did earlier. So then you will have V2 and V3, these as the degrees of freedom, and but theta z is only linear. So although it doesn't mean that in between theta z is 0, but as a degree of freedom it's only here theta z1 and theta z2. I am showing theta z rotation positive about z axis coming out of the screen. So now based on these considerations, we have said that V is taken as like B0 plus B1 x plus B2 x square, and maybe theta z is equal to C0 plus C1x. And in terms of shape functions, you can always write this as n1 into theta z1 plus n2 into theta z2, where n1 n2 are your 1 minus x by l x by l. And similarly for v, of course, you can always write in terms of shape functions. So we have derived, if you recall, for truss problem, we had derived the shape functions for a quadratic element. So it's the same interpolation and same approach, that v is v1 at node 1, v equal to v2 at node 2, v equal to v3 at node 3. So those quadratic shape functions, you can refer them back, because I am using n for this. So let me use a different notation here. So you can say m1 into v1 plus m2 into v2 plus m3 into v3. And now based on this interpolation, rest of the steps are going to remain same. You are going to substitute this approximation where m1, m2 are m3 are those quadratic shape functions which we had derived for the 3-noded truss element. So the same shape functions. And rest of then you write in the proper interpolation matrix and gradient matrices B, Bs and so on, and then you substitute into the integral functional, take its variation, you get the element level governing equation. So those steps remain same. So I am not actually repeating those, but you must try yourself once this. So this is what I had discussed. So again I reiterate the question, that in this case, if you want to eliminate shear locking, you have to take V as quadratic and theta z as linear, not vice versa. So maybe when you are doing your MATLAB programming in the lab class, it would be an interesting exercise if you take a beam problem, let's say fixed beam, and model that using Timasenko beam element with linear interpolation for both V and theta z, and try to see when you are using thin, that means compared to length, if the thickness is very small, and look at what kind of deflections you get, and then you model the same problem using this interpolation, and then check the results. So how they compare, and for thin beam, of course, you can always refer a textbook and see for a fixed beam, let's say under uniformly distributed load, what is the maximum deflection. So what kind of predictions you get if you use linear interpolation based CRD probable element, and this quadratic for V and linear for theta z, and then check the results. So I think you should do that exercise in your lab class. So this is what I had discussed under this consistent interpolation of V and theta z. And then so rest of the derivation you have to do. So the development of element level governing equations and so on, finally the derivation of stiffness matrix load vector, that of course you need to work on. Because the steps are same, so there is no point in I repeating same thing again. Talking about is the interdependent interpolation of V and theta z. So I think this is in fact ANSYS beam element is actually based on this particular formulation. So what it tells is interdependent means we have two variables V and theta z. So their interpolation is sharing some common constants, and that is why they are dependent on each other, and that is why this term interdependent interpolation of V and theta z. But then let us look at how we get to that. So we have already seen, so if you look at we have derived the equilibrium equations for beam. I am not considering the axial one, so only the bending part. So one of the differential equation was from the shear force. If you recall, it was d by dx of Ga into minus theta z plus dv by dx plus force along the y direction is equal to 0. So this was one differential equation, isn't it, for the Timasenko beam finite when we started with Timasenko beam theory. And the second equation was basically d by dx of Eizz, that is from the bending moment. So Eizz into d theta z by dx. This you can refer back your notes, it's there. We have done it earlier. And plus shear force here, which is Ga into minus theta z plus dv by dx is equal to 0. So these two differential equations we had derived. Now what we are going to do to derive this interdependent interpolation, we are actually going to make use of these differential equation considering the homogeneous form of these differential equations. So homogeneous, if we consider no, if we consider the homogeneous form of these differential equations, that means take the forcing terms to be 0, homogeneous form of equilibrium equations, and we will make one more assumption that within the element, so consider homogeneous form of equilibrium equations and constant EI GA within the element. So what we are doing here is within the element. So under this condition, we can integrate these equations basically and get the interpolation function. So what we want to do is integrate these. So when you homogeneous form means you are going to basically take, although when you are solving problems there would be load, but for the derivation purpose we are saying that let us take this 0. So when you take this 0, forcing term to 0, you call the resulting governing equations as homogeneous form of governing differential equations. And of course, as I said, EIZZ and GA you are taking constant. Now if you look at the structure of these equations, once I put y equal to 0, so if you look at this second equation here, so the first term of course is only involving theta z, and second term is involving your shear force. If I differentiate this equation once again, the second equation, so I will have second derivative here, and here I will have first derivative, and once we consider the homogeneous form of these equations, so first equation tells us that first derivative of this term is actually equal to 0. So now I can write for this equation combining both these equations together as d2 by dx square into EIZZ, and since EIZZ is constant, actually I can take out and eliminate it, is equal to 0. Is that right? So what I am doing, differentiating this equation once again, and so we will have the second term first derivative, and for the homogeneous case since Qi is taken as 0, so the first derivative of shear force is actually 0. So this term goes to 0. Here you get one more derivative because we have differentiated it once again, so we get this this particular quantity. Now what you can actually do here, that since EIZZ is constant, I can take it out and divide the whole equation by EIZZ. So finally what you would get is d cube theta z by dx cube is equal to 0. And now if you integrate this, so I know you will have to do the integration 3 times. So you will find that first time it is c1, this c1 x square by 2 plus you will have some c2x, let me put capital X, not small, I am using capital X. So this is capital X square and this is capital X plus c3. This is what I will get, right? So if I integrate this equation 3 times, this is what you get. So that means what you are saying that the interpolation for theta z is quadratic. So this is a constant term, this is a linear term, this is a quadratic term. So this is as far as theta z is concerned. Finally we want to get to basically V also. So now how do we get V? So for getting V, what we can do is again come back to basically this equation in the original form. So you follow, the first we are differentiating this equation, then from this equation the second term derivative we are putting it 0, so we get this, then we divide it by EIZZ, so we integrate it and finally get this as theta zz. Now let us again take the second equation, and now see in this case I am not going to differentiate it but going to consider it as it is, because now I have got theta z, so I want to get the interpolation for V. So then again if I consider the second equation, so what I can do is again, because EIZZ and GA they are constants, so maybe from this term I can divide it by EIZZ. So the second term would become d2 theta z by dx square and plus GA divided by EIZZ and minus theta z plus dV by dx is equal to 0. So this is what you will get. Okay. And now see, if you look at theta z, we have already got the interpolation for theta z, which is quadratic, and if you in the second derivatives, if you differentiate it twice, what you would actually get is only C1. So this would be just C1, and this is of course a constant, but it is depending on the shear modulus of the material, Young's modulus, cross sectional area, and the second moment of area, that is Izz. So G upon E into Izz and minus theta z here and plus dV by dx. This is equal to 0. If we want to get V, so we will have to take V one side and rest of the terms to the other side. So what we can actually do is we can now write this equation as you see, dV by dx from this equation can be written as, so first you take C1 to the other side, so you will have minus C1, and then now you multiply and divide by these terms, we will get Izz upon Ga and plus theta z. This is what you will get. It's just the manipulation of this equation. We want to get the expression for dV by dx. And now if you look at dV by dx is equal to minus C1 into, this is of course for the given problem it is going to be constant, and theta z is of course C1 x square by 2 plus C2x plus C3. So this is the interpolation for theta z which we already got. So this that I have substituted here, and now you can integrate it again once again with respect to x. So you get V is equal to, now this term will give you minus C1 into Eizz upon Ga into x, plus this would become C1 x cube by 6 plus C2 x square by 2 plus C3x plus C4. So now you see why we call the this kind of interpolation as interdependent interpolation, because when we are interpolating theta z within the element, that involves these three constants C1, C2, C3. So this is now the rather the usual way of interpolating V and theta z from by integrating the differential equation. This is the interpolation we are taking for theta z, and this is the interpolation we are taking for basically V. And this here these constants C1, C2, C3, one extra constant you have here which is C4. This kind of interpolation is referred to as interdependent interpolation. And of course you would see it's automatically satisfying the condition that interpolation for V is actually one order higher than the interpolation for theta z. So it is automatically coming, and with other parameter. And not only that, when we actually analyze this element in more details, we will find that this formulation will automatically become Euler-Bernoulli beam formulation when the beam is thin, and when beam is thick, essentially that is going to be governed by this ratio E into Izz upon Ga. So when the beam is thick, so you will find that Izz and A, they are going to be comparable. So this term will have basically significance. But when beam becomes thin, so your I involves H cube, and whereas A involves only H, so then I would become much smaller. So this term would actually tend to 0, and in that case you will find that just because only difference, see what is the difference. If you look at if I just look at theta z and if I look at dV by dx, so what is the difference? Difference is only basically this term. You would notice that when we look at dV by dx expression what we got here and theta z expression here, so if you just ignore the first term, that is this particular term, then dV by dx is nothing but equal to theta z, which is basically your Euler-Bernoulli beam theory. And this is the extra term. So if Eiz by Ga ratio is significant, so it behaves like shear deformable Timosenko beam, and if beam is thin, in that case Izz would be much smaller compared to A, that means this would be tending to 0. So the formulation actually automatically reduces to Euler-Bernoulli beam formulation without considering shear deformation. So that is the advantage of this. So the beam automatically, depending on the problem, the element would behave either as Euler-Bernoulli beam or Timosenko beam, depending on whether beam is thick or thin. So that is depending on this ratio Eiz upon Ga. Now of course at this stage the interpolations are in terms of these constants C1, C2, C3, C4. So we need to express them again in terms of the nodal variables. So since there are in all total 4 constants, so we need 4 elemental degrees of freedom in terms of V and theta z. So then when you formulate the element, that means when you express the constant C1, C2, C3, C4 in terms of elemental degrees of freedom, so you need to consider obviously a 2 x, this is y, and node 1 and node 2, and the degrees of freedom then would be, this is V2 at the second node, say V1, and the rotation theta z1. So now if we want to express C1, C2, C3, C4, what we will have to say, that now we look at the expressions of C1, C2, C3, C4 in terms of elemental degrees of freedom. So what you will do, now you need to use these conditions, that no V is equal to V1 at capital X equal to 0. So V is equal to V1 at capital X equal to 0. So that will give you, see if you look at the expression here for V, so when you put capital X 0, all these terms go to 0, so you will get C4 is equal to V1, so C4 constant. Then the second condition is this we have done earlier, the way we derive the shape function. So first we assume approximate solution in terms of unknown constants and the independent variables, say x, and then we express the unknown constants in terms of the values of the variable at node points. So now the next thing is that theta z is equal to theta z1 again at x equal to 0. So this will give you, so again if we look at the expression for theta z here, so we have x, when you put x equal to 0, this would be simply C3. So this will be then gives you C3 equal to theta z1, that means C4 is V1, C3 is theta z1. Then the third condition would be, these are not boundary condition, but we are just writing the equations to relate the unknown constants and the degrees of freedom, values of the variables at node points, which we did actually earlier. Then the third condition would be V equal to V2 at x is equal to small l, and this will give you of course then bit more complicated equation. So C3, C4 of course you have already got, what is left out is only C1, C2. So this equation will be giving you, say, V2 is equal to in terms of these constants. So the first one is minus C1 into EIZZ upon GA into L, that is the first term, and then you have of course the other terms, which is C1 L cube by 6 plus C2 L square by 2 plus C3 into L plus C4. Out of this, C3 and C4 you have already got, so you have one equation in C1 and C2. The last equation for C1 and C2 would be theta z is equal to theta z2 at x is equal to L. This is actually what we are doing is, once we understand that what form of polynomial to be taken for V and theta z, rest is the mechanical process, standard procedure of finding out shape functions in terms of the coordinates and expressing the interpolation in terms of values of the variable at node points. So theta z is equal to theta z2 will give you another equation, that theta z2 is equal to, you substitute this here in this particular equation, which is C1 L square by 2, C1 L square by 2 plus C2 into L plus C3. So C3, C4 you already got. So what you can do, using these two equations you can find out your C1 and C2, and once you get C1, C2 also, C3 together with C3 and C4, so you put values of C1, C2, C3, C4 here. Similarly put the values of C1, C2, C3 here, collect the coefficient of V1 theta z1, V2 theta z2, you will get your 4 shape functions. So this you can complete this exercise of finding out finally the shape functions in terms of values of the variable at node points, that is finding out C1, C2, putting into the expressions for V and theta z, and then rearranging those, collecting the coefficient of V1, theta z1, V2, theta z2. So you will get set of shape functions, and you would see the advantage here is that the element still has got no 4 degrees of freedom, or at each node only V and theta z, and we have advantage of having Timoshenko beam considering the shear deformation, as well as for thin cases it is behaving like a Euler-Bernoulli beam formulation. So that is the advantage in this case. So the remaining exercise you can do, right. So finding out C1, C2 also, putting back into these two expressions, then collecting the coefficient of each of these V1, theta z1, V2, theta z2, we will get shape functions for V. Of course, these shape functions, the expressions for shape functions for V and theta z. So you would get finally V is equal to something like this. Let me write, let me say the first set of shape functions as n1 or whatever notation you want to use. So it would be like n1 V1 plus n2 theta z1 plus n3 V2 plus n4 theta z2, but theta z now is not the same thing, but it will have, let us say, some m1 V1 plus m2 theta z1 plus m3 V2 plus m4 into theta z2. So this is something what you will get. You need to get the expressions for n1, n2, n3, n4, m1, m2, m3, m4. Some terms would be common, there would be some differences, and you would see, of course, the shape functions are going to be now in terms of, they are not only in terms of x and L, but they are also going to be in terms of this parameter Eizz upon Ga. So now your shape functions are no longer just the in terms of independent coordinate x and length of the element, but the shape functions are also in terms of material properties, Young's modulus, shear modulus, and the cross sectional properties Izz and A, cross sectional area and area moment of inertia. So once you derive this, and then of course you again substitute back in your integral functional, and you can derive the element level Gaussian equation. For you to cross check, I have got this stiffness matrix for this element. So you can finally cross check the load vector, of course you can derive, and the internal load vector remains same, minus S1 minus M1 S2 and M2, if you are not considering U naught. So K is based on this interpolation. When you do the evaluation of both the energy terms, which is bending energy and the shear energy put together, when you combine, finally this stiffness matrix comes out as, see this Eizz. This is so that when you derive you can actually cross check that shape function, and then finally when you get to the stiffness matrix you are right. So this stiffness matrix, there is one parameter defined, I will define at the end. So this is 12 divided by 1 plus, there is a parameter phi, I will define what this phi is, 6L upon 1 plus phi, and then you have minus 12 upon 1 plus phi, then you have 6L upon 1 plus phi. That is the first row, and then of course it is symmetric, so let me only write the upper half. So 4 plus phi into L square divided by 1 plus phi is this element, then you have minus 6 into L upon 1 plus phi, and then this is 2 minus phi L square divided by 1 plus phi, and then this is 12 upon 1 plus phi, and this is minus 6L upon 1 plus phi, and the last is here 4 plus phi into L square divided by 1 plus phi, and of course it is symmetric, so the other you can fill up. So there is this, these are no symmetric terms, we can just get that. For this phi is here taken as 12 into Eizz divided by G into A into L square. So this is how you get the stiffness matrix. The load vector you can derive, the consistent load vector, and then you have the final element level Gaussian equations based on this element. And this is what I was saying, that when you do your MATLAB class, lab class, you can actually experiment with both the elements, the standard one with linear interpolation for V and theta z, maybe with this element, and maybe with also the consistent interpolation with V as quadratic and theta z as linear. So the remaining exercise you must do. Okay. So then the third aspect is, so is this clear how we are getting the basically we are deriving these shape functions from differential equations, and obviously differential equations are basically connecting the two variables b and theta z, so we get the interconnected or interdependent interpolation, and the advantages I already discussed. The third method to eliminate shear locking was reduced integration. So what is the meaning of this reduced integration? Any guess? What could this mean? Reduced integration. Yes. So what could this reduced integration might mean? It says reduced integration. So what could it mean? I am just asking a question to all of you. Pardon? Reducing the order of integration. Yes. Any other guess? Okay, big form also, of course, we do the integration by parts and reduce the differentiability requirement. So yes, so that's the second answer. There should be some more answers. At this stage, you are making a guess. So it's like brainstorming session. No, you can make any guess. Yeah, and so one of these reducing the number of constants, maybe in the interpolation. Okay, let us say like that. Yeah, okay, so reducing the power of variables, say for example x, you use lower powers. So now there can be many answers, so let us look at it, what it is really. So this integration means here we are talking of when we evaluate the stiffness matrix, so we are doing integration there. So the integration is actually referring to the integration for evaluating the stiffness matrix. So for this standard two-noded Timoshenko beam element, we had taken linear approximation for v and theta z, wherein we had basically this as x and this as y, and the degrees of freedom at these two nodes are here. You have just v2 and theta z2, and here you have theta z1 and b1. So this is the interpolation, and so let me write the essentially the expression for Ke. So the element level governing equation, rest of the procedure is same. I am only taking, I have taken out here u naught, so that you should be able to do to get into this. So the element level governing equation then in a standard approach with linear approximation for v and theta z would be Ke dE is equal to f external for the element and plus f internal. So this is the same standard form. Out of the in this we see the Ke, the element level stiffness matrix, is integration from 0 to L, and if we take out the axial deformation part, the stretching of the centroidal axis or the neutral axis, then this term would be simply EIZZ into you will have that B matrix, the only theta z part of that B matrix. So let me still put it as B transpose B into dx. So this was coming from the bending. I have just taken out the axial part. So this is what you will have if you are only having the bending part, no axial deformation, no axial load. And the second term would be integration 0 to L GA, and here we had this BS transpose into BS into dx, isn't it? You remember, this is we have already derived this. So see, now we know to evaluate these matrices, we need to do the integration. So one way of doing the integration is explicit integration, that we multiply all the quantities and then we integrate each term one by one, and then finally if we do that, what we get is actually the exact integration. That means we are evaluating these integrals exactly. So the meaning of reduced integration is that we don't want to evaluate these integrals exactly, but we want to evaluate them somewhat smaller than what exact integral would be. So reduced integration means we want to under evaluate these integrals, but then that we do not do for both these, because the problem is not because of this, the locking problem is here, because this is coming from your shear strain energy, which is your gamma xy minus theta z plus dV by dx. So this energy term, this stiffness term actually has come from shear strain energy. So the reduced integration means we want to under integrate this. So when the beam is becoming thinner, if you are not exactly integrating but you are under integrating, so whatever locking is happening, so locking can also be interpreted as spurious increase, unrealistic increase in the stiffness of the structure, and that increase is coming from this part. So if you integrate it, under integrate it, so whatever increase is happening, that will not happen, you suppress that. So that is the meaning of this reduced integration. But then how do we do it? So that can obviously, we cannot do if we are doing the explicit integration. Explicit means you multiply all of them and then actually do the integration. X integral is x square by 2, x square is x cube by 3, and put the limits and so on. That's your explicit integral. But what we want to do is that another way of evaluating these integrals is through numerical integration. So I will briefly introduce this numerical integration when we go to 2D problems and talk of formulation in natural coordinates, isoparametric formulation and so on. That I will discuss this in more detail, but today let me just briefly talk about this numerical integration, and then I will say what is this reduced integration. So numerical integration meaning is, let me first say in terms of a variable which is varying from -1 to +1. So if I want to evaluate an integral say from -1 to +1, some function which is a function of this variable xi d xi. So that means here this variable xi is a variable which varies from -1 to +1. So the integral -1 to +1 f xi d xi can be written as, like you would have done Simpson's rule, trapezoidal rule for integration. This is somewhat similar to that. So same thing here, what we are saying is that rather than explicitly evaluating this integral, we want to evaluate this numerically. So in the numerical integration, then what we do, now replace this integration by summation, and says there are certain number of points here, I going from 1 to 1. So what I will do is I evaluate this function at n number of points, and now this d xi is written as a kind of a weight factor. So it's not a weighted in case of weighted residual statement, whatever weight functions we have got, so it's not that weight function. This is going to be actually numerical value. So this is a weight factor. So what you are doing is you are evaluating at n number of points the function, multiplying a weight factor, summing them all together, and after the summation whatever you get is representing basically this integral. So this we call as numerical integration. And now to evaluate different kinds of functions. So if this function is say linear, or if it is quadratic in xi, or it is cubic in xi, this n would change. So here there is a nomenclature. Usually we call xi I as the integration point, because this is the value of xi at each point where we are evaluating the function. So xi I is referred to as integration point, and wi is referred to as weight factor, and n is the number of integration points. Okay, so I think there is some class here. I thought of completing this number of integration points. So typically, see if I use I equal only 1 point. So for n equal to 1 case, I will have only one xi 1. Xi 1 is actually then comes out to be 0. There is a derivation for this which I am not discussing, and weight factor comes out as actually 2. That if I take 2 integration points, that is this number of points, one case is n equal to 1. If I use n equal to 2, that means I evaluate the function at 2 points, they multiply by the corresponding weight factor, then I get the integral. So for n equal to 2, then you will have 2 integration points. So xi 1 comes out as -1 upon root 3, and the corresponding weight factor is 1, and xi 2, the second integration point, comes out as 1 upon root 3 plus, this is minus, this is plus, and w2 is also equal to 1, and so on. So you have, if you use n equal to 1, it's 1 point integration. If you use 2 points, it's 2 point integration. If you use n equal to 3, 3 point integration, and so on. Now how we decide? So we have now actually these these points whatever I have written, they are actually for Gauss quadrature numerical integration. So we also call these as xi 1 values as Gauss points, and these are the corresponding weight factors. So now also see if how do we decide what should be n? So n depends on what is this function. So if it is a polynomial, and if the highest power of xi in this polynomial is, let us say, m, small m, then you need approximately n is equal to, see if f xi is, let us say, polynomial is something a0 plus a1 xi and like that plus say am into xi to the power m, then n should be approximately, so this is an approximate expression, m plus 1 by 2. So if you want to evaluate this integral actually exactly using numerical integration, then you need to use m plus 1 by 2 point. So if it is a linear, just simply a linear, f xi is a linear function, that is simply a naught plus a1 xi, then m equal to 1, 1 plus 1 by 2, so actually just 1 point would be sufficient. So if you have a linear function, evaluate the value of the function into 2, you will get actually the integral whatever you would get. And if m is equal to, let us say, 2, it is a quadratic function, then it is 2 plus 1 by 2, so it is 3 by 2 approximated as next integer, so 2 points, n equal to 2. So now what we have here is, we are talking of is the integration 0 to L. So if you have any other integrals, say integral general case a to b f of x dx, so this you can convert, again you, through the transformation of the variables, you can convert this into the same kind of a problem. So you can write this also in a similar fashion, that I going from 1 to n, f evaluated at xi and into, let us say, wi bar. I am using for this x separately, where your xi would be whatever we have got there. So you can write this xi is or the relationship between x and xi would be, I can write a general relationship. So here x then would be equal to the lower limit plus upper limit by 2 plus b minus a by 2 into the detailed derivation I am not doing at this stage. I am giving you only the formula to bring in the context of this reduced integration, and then your corresponding, basically as you see, wi bar would be equal to b minus a by 2 into wi, and wi means whatever I have written here, those are your wi's. So now if you, so is this is a brief about the numerical integration we are referring to. More details we will do when we talk of 2D problems. Now first thing, if you look at this particular expression, so if you look at this particular expression, essentially Vs for a linear interpolation of V and theta z, what would be the highest power of x in Vs? Vs is minus theta z plus dV by dx, theta z is linear in x, ultimately in Bs highest power of x is going to be 1. When you do Bs transpose into Bs, in the multiplication what would be the highest power of x? Would be 2. So if you want to exactly integrate that numerically, you need highest power is 2, that is your small m, what I was talking about here is actually 2, so 2 plus 1 by 2, 1.5 essentially approximated to 2. So if you want to actually integrate this energy, the stiffness contribution from transverse shear energy, you need to use capital N equal to 2. So you will get two values, x1, x2 corresponding w1 bar, w2 bar, evaluate the this whole of the matrices, multiply them and sum over those 2 points, you will get finally the exact value. Now we want to do here reduce integration. So reduce integration is one order less. So one order less means then we do the integration only using 1 point, n equal to 1. So when you evaluate, that is known as reduced integration. So when we do that, that means now only one integration point, you are underestimating this integral, and when you underestimate this integral, actually it overcomes the locking problem. So this you would still go by whatever order of integration is needed, but for the evaluation of this you would be doing the reduced integration, that is integration one order less, what is needed. So you need actually 2 integration points, but rather than using 2 you will use 1, and if you do this, then your element also behaves well for thin problems. But now if you this technique is using the reduced lower order of integration for evaluating the transverse shear strain energy, transverse shear stiffness contribution to the total stiffness is known as reduced integration technique for eliminating shear loss. Advantage is that when it's a simple to implement, because what you are doing is of course only thing, rather than explicitly integrating, you are doing the numerical integration and you are not making any changes. You have the same kind of interpolation for both V and theta z, and then you are working out the stiffness matrix. But the and when you use now this formulation for thin problems, it eliminates shear locking and it gives you accurate results. But when you use this for thick problems, then in case of thick problems, you are actually underestimating the stiffness, and locking is actually not there. So then your results would be then over, your deflections would be actually over predicted. So because its stiffness is reduced. So when you are using reduced integration, you should be using that only for thin problems and not for thick. So if you are anticipating that the problem is actually a thick beam problem, then you have to use the full integration for this. And if you anticipate that the problem is a thin problem, there is a locking happening there, then you use the reduced integration for this. The integration one order lower than what is needed to get the exact integral. So this is known as reduced integration. So these are the three ways we can overcome the transverse shear locking in the shear deformable Timoshenko beam finite element when we are using this for thin problems. Of course, the other two formulations, the consistent interpolation and the interdependent interpolation, same formulation. There you are exactly integrating and getting the stiffness matrices. Same can be used for both thick as well as thin problems, will give you correct solution. So I stop here, and then now we will meet only after the mid semester break. So meantime, now do all the derivation in between whatever I have left, because that's part of your total course evaluation. So if you have any doubts or questions, you can actually ask outside. Yeah, Babu, collect the assignments. Yeah, today you also need to submit the assignments.